Yeah, welcome back to Facilities Design and Logistics course, and we continue our discussion on rectilinear facility location models. And here I will start by solving an example to demonstrate how to sketch these isocost lines. So let's consider this example in which there are 4 facilities. Their coordinates are given and their weights are also given. Okay, first I'm going to solve this example as a continuous facility location problem with rectilinear distance to minimize the sum of the distances. And then I will find the optimum location x and y coordinates, and then I will sketch the isocost lines. Okay, so remember what we do for the x coordinate. We start with our procedure with the x coordinate, and I need to order the facilities with respect to their x coordinates. And as you can see, P1 has a coordinate of 4, P2 it's 8, P3 it's 11, and P4 it's 13, and the corresponding weights are 1, 2, 2, 1, and the sum of these weights is 6, and 1/2 of the weight is 3. Then the partial sum of the weights, if I write it here, for the first one it is 1, and as you can see it is less than 3. The partial sum here is 3, which is equal to 3. Okay, so last time we discussed this. When it is equal, yes, it is optimal. Okay, it is optimal, but there are alternative optima, and the alternative optima starts from x coordinate 8 and moves until to the next one, where this partial weight is strictly greater than the half. So if I continue, the partial weight here is the sum of these weights, which is 5, and it is strictly greater than 3. So it means that the alternative optima is between 8 and 11. So x star, you can represent this alternative optima like this. It's an element of this range, 8 and 11. Okay, so this is x coordinate. What about y coordinate? Again, we need to order them, and we see that there is this coordinate of 2 for which there are P1 and P4, okay, at the same coordinate. Then the coordinate is 5 for P2 and 8 for P3. And the weights here, the partial weights for the first one, it will be the sum of these two because they are on exactly the same coordinate. So it will be 2, 2, and 2, and again their summation is 6, and when I divide it by 2 it is 3. This will always be equal because I'm using the same weights. And the partial weight, the partial sum, is here 2, which is less than 3, and this is 4, which is greater than 3, and this is the first coordinate that this partial sum exceeds the half of the weight. So it means that the optimal y coordinate is 5. So any point on the coordinates, so if I sketch the coordinate system like this, x and y, so let's say this is 8 and this is 11, and y equal 5 is here. Okay, so any point on this line segment over here is optimal. You can locate your facility to here, to here, to here, to here, anywhere, and it will have exactly the same optimum location. Now assume that it is not possible to locate your facility to here, to this region. It's not possible. There is some kind of a restriction there. Then what can we do? We can follow the isocost contour lines procedure. And for this example, let's use these 6 steps procedure to sketch the isocost lines. Okay, what do we do? Initially, in the coordinate system, we sketch the existing facilities. So the first facility is in coordinate, let me see, 4 and 2. So let's say that this point is 4 and 2. Okay, then the next facility P2, where is it? It is 8 and 5. So assume 8 and 5 is somewhere here. This is 8 and this is 2, this is 5. Okay, and then P3 is 11 and 8. So 11 and 8 maybe somewhere here. This is 11 and this is 8, and next one is 13 and 2. So 13 will be here and 2 will be here, and this is P4. Okay, so we have these 4 facilities. This is P1, P2, P3 and P4. And next step is to sketch horizontal and vertical lines passing through these coordinates. So at this coordinate of 2, there is one horizontal line, coordinate of 5, horizontal line, and 8, this horizontal line. And then vertical lines for 4. So I am trying to sketch this as straight lines. Okay, 11 and 13. Okay, now we have these grids. Okay, the enclosed ones are grids, as well as the ones here on the left, top, or on the right, they are also the grids. Okay, next step is to write the weights corresponding to each one of these vertical and horizontal lines, and for this reason I will try to use a different color to not to confuse with the coordinate axis. So here on this vertical line, first vertical line, we have P1, right? So the weight of P1 is 1. So the weight corresponding to this is 1. I'm going to write it in parentheses. The second vertical line, it is P2 and its weight is 2. The third one, it is P3 and its weight is 2. And the fourth one, P4, and its weight is 1. Okay, what about the weights on the horizontal lines? This first one, there is P1 and P4. Don't do this mistake, don't write just one of them. I need to write the sum of them, P1 and P4, and their sum 1 plus 1 is 2. Okay. In the second one, there is P2 and its weight is 2, so I'm writing here 2. And in the third one, we have P3 and its weight is 2. Okay, now I need to calculate the net pull for each column over here. Let me use a different color. So first, I am going to consider this column over here. To the left of this column, there is nothing. And to the right of this column, we have all other weights, which sums up to 6. And I know that pulling to the right is negative. So this row, this column over here, has a net pull value of -6. Okay? So the second one, let's consider the second one. To the left of this one, I have 1, which is plus. and to the right of them I have minus 5, so it makes minus 4. Okay, this one, to the left I have 3, to the right I have 3, it means that it is 0. And this one, to the left I have 5, and to the right I have 1, so left is positive, right is negative, it means that it will be 4. And the last one, to the left I have 6, to the right I have nothing, so it will be plus 6. Okay, so these are the net pull values for the columns. Now I need to do the same thing for the rows. And for this one, as you can see, to the bottom, to down there is nothing. To up, 2 plus 2 plus 2, it is 6. And pull towards up is negative, so it means that this is minus 6. For this one, down 2, up 4, so it will be minus 2. For this one, down 4, the sum of these weights, 4, to the up I have 2, and the net pull will be 2 because down is positive, up is negative. And this one, there is nothing to up, all is down, it means that it is 6. So this is, these are the net pull values for each row and column corresponding to these grids. The next thing is to calculate the slopes for each grid. Okay, so let's start from this one over here, this grid. Although it is not enclosed, it is still a grid. Okay, so we need to consider that one as well. So what is this value? It will be the column value divided by row value, and don't forget the negative sign. Okay, minus 6 divided by 6, but there is another minus in before, so the slope here is 1. So I'm going to represent these slopes in each region within enclosed circles. Let me write it. So this is 1. What about this one? This grid over here. Okay, I will first move towards right and then fill in all those values. So this will be minus 4 divided by 6, and take the negative, it will be 4 over 6, or simply 2 over 3. So this one, 0 over 6, it will be 0. Negative is also 0. Okay, look, remember, this 0 means the slope of the line in this grid will be 0. What does slope 0 means? It is a horizontal line, okay? So remember, if this is your coordinate system, if a line has 0 slope, then it will be parallel to the x-axis. In some cases, instead of this column value, we may have 0, for example, in a row. And corresponding to this row, if you divide, for example, 6 by 0, it will be infinite. Okay? And what does slope infinity means? It will be a vertical line. It will be parallel to the y-axis. Okay? So don't be confused. We may have 0 or infinite slopes as well. In this example, we have 0 slope, and it means that those lines in this grid will be parallel to the x-axis. Okay, the next one, it will be 4 divided by 6, but it will be negative, minus 2 over 3. And the next one, 6 plus 6 and negative, it will be minus 1. Okay, next one, minus 6 divided by 2 with a negative sign, it will be 3. Okay, this one. So please try to follow me by calculating yourself. minus 4 divided by 2, negative of that, it will be 2 here. This will be 0. The next one will be 4 over 2 negative, and the next one 6 over 2 negative. Okay, next one, minus 6 divided by minus 2, 3. Take the negative, it will be minus 3. Minus 4 divided by minus 2 with a negative sign, so it will be minus 2. This one will be 0. This one will be 4 over minus 2 and it's negative, which will be positive 2. And 6 divided by negative 2 and it's negative, it will be plus 3. And the next one, minus 6 and the negative 1, it will be minus 1. Minus 4 minus 6, it will be minus 2 over 3. This will be 0. This will be 4 over minus 6. It will be 2 over 3. And the last one, it will be 6 over minus 6. And take the negative, it will be 1. So we calculated all the slopes. But it is not over yet. We just calculated the slopes. How shall we sketch the contour line? Okay. For this reason, what we are going to do, or what we need to do, is we need to find a starting point. Find a starting point. Okay, let's assume that we start from this point over here. I just selected this point, okay? Sometimes in a question I can give you this. I can give you start from this coordinate and sketch the contour line. And actually, what do we know about this point? Do we know the coordinate of this point? We know that the y coordinate of this point is 5. It is on this line. So the y coordinate is 5 and the x coordinate will be between 4 and 8. Let's say it is 7. Okay, so let's start with coordinates 7 and 5 and sketch this contour line. So you can continue up or down the grid on the up or down. Let me start by going up. So I am in this grid now, and I know that in this grid the slope is 2. And again, remember, when the slope is positive, it will be a line like this. Okay, so this line passing through this 7 and 5 will be a line like this. And the slope of this line should be 2. When I say slope, it is y divided by x. Y value divided by x value should be equal to 2. So, do we know this distance over here? Yes, actually, because we know that the x coordinate here is 7 and the y coordinate here is 8. And this distance over here is 1. Then, can we find this distance over here? Yes, the slope must be 2. Therefore, this distance here should be 2. So that 2 over 1, it will be 1. Okay, if this distance is 2, then what is the y coordinate of this point? Can you tell me? So 5 was the y coordinate of this line, and I am moving 2 units up, so it will be, the y coordinate will be 7. And what is the x coordinate of that point? Look, the x coordinate of this line is 8, so it is coordinate 8 and 7. Okay, so starting from point 7 and 5, the next location, the next point that I crossed, the border of the grid line is 8 and 7. Okay, so this is the procedure actually. We will follow this procedure until we close this loop. The next one, the next grid is this one. I am in this grid now. So where should I go? Since the slope is 0, it will be a parallel line. Okay, So a parallel line will go something like this. So, and can we find the coordinate of this one? Yes, because since it is parallel, the y coordinate will not be changed. It is 7. What about x coordinate? X coordinate I already know. It is 11. So this coordinate is 11 and 7. Okay. Next, I am in this grid now. And in that grid, the slope is -2. Okay. Remember, in this one, the slope was +2. Here, it is -2. Since it's negative, the line will be something like this. And I know the y coordinate here. I know this distance. It is 7 minus 5. It is 2. And in order this slope to be equal to -2, then this distance over here should be 1. And it means that starting from 11, this coordinate will be 12. So it will be 12 and y coordinate is 5. Okay, so this is the next grid that I intersected, the border that I intersected with. Then the next slope, let me write this slope here, this side of this grid is +2, +2. So since it is +2, the line should be something like this in this grid. And I know this distance to be 1, then in order to have the slope to be 2, this y distance should be equal to 2. Okay, starting from 5, I am going 2 units down, so it means that this coordinate is 11 and 3. Okay, the next grid is 0 and the slope is 0. It means that I will move parallel to the x-axis and I will be hitting this borderline, and its x-axis is x coordinate is 8 and y coordinate is 3, the same with the previous one. And in the last or final grid, the slope is -2. -2 means that we will be moving, let me clean up some space here. We will be moving towards left and up. So you can try it, but I can guarantee that it will be closing the loop by moving to the same coordinate again. Okay, then we enclose this loop. This is a contour line, and on this contour line, wherever you locate your facility, it has the same cost, exactly the same cost. And what is that cost? Actually, just put 7 and 5 into your objective function and you can find that cost. And you can try it, just put 8 and 3 into your objective function equation and you should be finding the same cost value. You can select any coordinate on this contour line and that cost will be the same. Remember, what was our optimal solution for this example? X coordinate, there was alternative optima. Optimal x was between 8 and 11 and y coordinate was 5. And where is that in this shape? Actually, it is this line segment over here. This is the line segment for optimum locations, and as you can see, this contour line encloses that optimal location. But you can say, okay, why did we started from 7 and 5 as the initial coordinate? We could have started on another location, another coordinate. Let's say it can be something here. In that case, how shall we sketch the contour line? And you will do exactly the same procedure. So starting from here with a slope of 2 units, you will be moving here. Okay, but as you can see, this time we are not going to this grid, but we are going to this grid. We are entering to a different grid. So you need to be careful about these coordinates, in which grid you are actually entering into. And if you enter into this grid, now as you can see, the slope is changing. This was 2, this is 2 over 3. 2 over 3, it is more closer to the x-axis. I mean, not that steep as 2. Then you will be entering into this one, and here you will be going parallel and entering into this grid. And it has negative 2 over 3. It means that it will go, it will go into, it will go into this one, and then it will enter into the other grid in which the slope is negative 2. It will go to here, and then positive 2. It will go to here, and then 2 over 3, and then 0, and then negative 2 over 3, and then negative 2, and enclose the circle. I didn't, calculated all the coordinates for this one. Of course, while sketching it, you have to do it. You have to find all these intersection points. And as you can see, it requires a lot of, calculations. But the thing is, it's doable. And it gives you some idea. You should be able to follow this procedure. And again, even you can select other coordinates, and here it is 2. It means that you are going to here, and then to here, and then to here, to here. So to here with negative 1 here, and then to here, positive 3, and then 1, and then 2 over 3, and then parallel, and then minus 2 over 3, and then minus 1, and then minus 3, and enclose the circle. Okay? In this example, the contour lines should be looking like this. Even you can sketch contour lines in between. So what will be the shape of a contour line in between here? It will go to here, and then to here, and then to here, to here. It will be inside those two contours. And there are infinitely many contours in between these contour lines. The shape, as it expands outwards, the shape changes a little bit, but they never intersect with each other. The contour lines never intersect with each other. And look, in this problem, if you have, let me use a different color. What colors I didn't use? Assume that this region over here, there is your existing facility in which you cannot locate your new facility. Okay, this area is forbidden. Then where you are going to locate your facility? So you will locate your facility to the location or to the coordinate on the border of this restricted area, which intersect with one of the contour line, which is in the inner contour line. Okay? So for example, on this example, this contour line over here, if this contour line is out of the restricted area, then your optimal location will be this one. Otherwise, if it is in the region, then this intersection over here will be your next best alternative. Okay? Like this, you can identify the coordinate of the next best solution. This is the procedure. So, until now, we focused on single facility, rectilinear distance, minisum location problems. Okay? Now, we are changing our objective, and we want to minimize the maximum distance. Okay, it's a very important objective, especially in certain situations like emergency facilities, locations, and etc. For example, if you want to locate a fire station or an ambulance or an emergency medical service, you want to reach your customers within a certain amount of time, not exceeding, for example, 15 minutes, in less than 15 minutes. In this case, you don't want to minimize the sum of the distances, but you want to minimize the maximum distance. So we can represent this objective function like this. Okay, we are still interested in the rectilinear distance. So it is x minus ai plus y minus bi. But we want to minimize this maximum distance. Sometimes we represent, we include another constant like gi into this. What does gi represent? Assume that in order you have a multi-floor facility. For example, it has 5 floors. And your emergency facility, let's say, is located in the first floor. And it will be serving all other floors, second floor, third floor, and etc. And in order to reach these floors, you need to use elevator to move to that floors. And that elevator, the time or the distance that you cover in that elevator is always the same. So you move, for example, 10 meters up or 2 meters up, and then in that floor you are going to the coordinate of AI, BI. So let me try to sketch it like this. Let's assume that this is your first floor and this is your second floor. They are not side by side, of course. And there is this elevator from this first floor. It moves exactly to the same coordinate in the second floor. Okay, this elevator, let's say the distance is 2 meters. And your emergency service, okay, actually you want to locate this elevator, let's say, and then your existing facility is at this coordinate. So what is the total distance? It is the distance that it takes with the elevator plus this distance to the facility, AI, BI. So if that is the case, we implement or we use this GI. Sometimes GI is given to us as 0. There is no such time that you move, such distance that you move all the time, but sometimes there is. So this is the compact form of writing it. Let me try to write it in open form. For an example, let's say that our P1 first facility is in coordinate 1, 1. Then another facility in 5, 2. And let's assume another facility, sorry, P3 in 3 and 8. Okay. And we want to locate a single facility to minimize maximum distance and assume G1, G2, G3 for all these facilities are 0. Okay. Now, how do we write our objective function? It will be something like this. Minimize, we want to minimize the maximum of, let me write in a large parenthesis. So it will be x minus 1 plus y minus 1 absolute value. This is the distance to the first facility. Let me write it in a better way. Okay. Okay. And then we will take the maximum of this one, or x minus 3 plus y minus 8. Sorry, let's write to the P2 first, then P3. So x minus 5, y minus 2, and x minus 3 plus y minus 8. Okay, so we want to minimize the maximum of this 1, 2, 3 values. There are 3 values and we want to minimize the maximum of them, these. And in this question, observe one thing, we don't have VI in front of them. We don't have the weights. Actually, you could have written, you could have these weights. But the thing is, we will learn a solution procedure to solve such problems, and in that solution procedure works only if there are no such weights, or if all the weights are equal to 1. So our assumption here is Vi is equal to 1 for all I, so that we ignore it. Okay? So this is the min-max objective function, and we will be learning a method to solve this problem with min-max objective. So I explained GI, and the procedure is this. Simply using the coordinates of the existing facilities. AI is the x coordinate, BI is the y coordinate of existing facility I, and this GI is the constant fixed travel associated with this existing facility. And using these, we will be calculating 5 values: C1, C2, C3, C4, and C5. And look, C1 is calculated as the minimum of AI plus BI minus GI. C2 is calculated as the maximum of AI plus BI plus GI. So what does it mean, the minimum or maximum of this? Look, we have I indices over here. So how many existing facilities you have? In the previous example, we had 3. So you will be finding these values for the first facility, comma, the second facility, comma, the third facility, and you will be finding minimum of them, and it will be your C1 value. Similarly, you will do the same thing with this calculation. It will be your C2. Calculate this for 3 facilities, and it will be your C3, C4, and C5 in the same way. Then, when you calculate C1, C2 up to C5 in this way, the optimum facility will not be a single location, will not be in a single location, but it will be on the line segment. Okay, it will be on the line segment connecting 2 points. Okay, in this coordinate system, let's say you will find one coordinate x1 star and y1 star, and you will find another point which will be your x2 star and y2 star, and your facility can be located anywhere on this line segment, anywhere. There are alternative optima. And how do you find x1 y1 star? It is 1/2 of this is x coordinate, okay, and this is y coordinate. And when I say 1/2, it actually you simply divide this value by 2 and this value by 2, and this is your x coordinate and this is your y coordinate for x1 and y1 star. Similarly, the second location, second point, will be C2 minus C4 divided by 2 for x coordinate, and for y coordinate you have this, and any point connecting these two will be your optimum location. And there is one more observation here. These are the locations of the optimum optimum locations of your facility. And what is your objective function? Your objective function is simply C5 over 2. So in the previous slide, we calculated these constants or parameters C1, C2 up to C5. And the maximum distance, remember this is your objective function, and your maximum distance is C5 over 2. Okay, this is the procedure. And I will stop at this point. We will be solving examples to better understand this one.